Okay. All right. So I'm recording now. I'm going to go ahead and share my notebook screen with you. And we'll work some problems. Okay. So you should see my notebook. And remember, this is 12.4. We're just continuing with the implicit stuff. Okay, so let's do a review question. Sorry, an example of what we did last time in class. So, for example, if I have an equation, maybe I've got x squared plus y cubed equals 7. And in the question, I want to find dy dx, or find the derivative of the function. But remember, the function is defined implicitly, which means y is not solved for. And that's okay. And we don't solve for y first. We just start taking the derivative of each term in the equation as it is. So we take the derivative of x squared and we get 2x. We take the derivative of y cubed. So remember, when you're taking the derivative of y, you treat it like it was x cubed. So just treat it like it's an x for a minute. If it was x cubed, it would be 3x squared. So y cubed becomes 3y squared. But because it's a y and not an x, we add on the dy dx term. And then on the other side, the derivative of 7 is 0. Now from here, remember, after you take the derivative of each term, all you have to do is solve for dy dx. So just get it by itself. So I'm going to subtract 2x from both sides here and get 3y squared dy dx equals negative 2x. And then let's divide both sides by 3y squared and get dy dx equals negative 2x over 3y squared. And that's all we can do because we don't know values for x and y, right? So this is what we did last time. Take the derivative of everything and then just solve for dy dx. Here's what's going to be a little bit different today. So I'm going to use the same example, but I'm going to add something to the instructions. So I'm going to stick with the x squared plus y cubed equals 7. This time I want to find dy dx at a point. So let's do at the point 0, 1. So you guys, when I have a point that I want to find dy dx at this given point, so what it means is when I'm taking the derivative, I'm going to do that just the normal way. But after I take the derivative of each term, I'm actually going to put the point 0, 1 into the equation and then solve for dy dx. So our first step actually looks just the same. So we will deal with this at 0, 1 in a second. But you guys, your first step is still take the derivative of every term. So on the first line, we're still going to get 2x plus 3y squared dy dx equals 0. But here, because I do have a specific point that I want to evaluate this at, now I'm going to put, now this point, I know that x is 0 and y is 1. Now that you've taken the derivative, put a 0 in for any x and put a 1 in for any y. So we can't put 0 and 1 into the original problem. You have to take the derivative first and then put in 0 and 1. So if x is 0 and y is 1, then this looks like 2 times 0 plus 3 times 1 squared dy dx equals 0. Notice that this whole term here goes away because x is 0. What I'm left with is just 3 dy dx equals 0. And then I need to divide both sides by 3 to get rid of the 3 on the one side to isolate dy dx. And I end up with dy dx equals 0. So notice the difference in these two things. Over here, I just said, hey, I just want you to find the derivative. So remember, dy dx is just the derivative of the function. I want to just find the derivative in general. And then I got this term with x and y's in it, and that's my answer, right? But when I want to find the derivative at a certain point, remember what the derivative is at each point. It's like the slope of the tangent line at each point, right? So when you find it at a point, it's just a number. So it makes sense that when you put numbers in for x and y, your answer is also just a number. Notice that on this side here, where we have the negative 2x over 3y squared, if we had put in, so maybe we had done this problem and then I said, oh, now find it at 0, 1. Well, you've already solved for dy dx here, but you could still then put in 0, 1, and notice you would get the same thing. It's just over here, I put in the 0 and 1 before I isolated dy dx, and it really doesn't matter which way you go. What we're going to see in our problems today is that isolating dy dx can get pretty tricky algebraically. Here, let me finish this off. So if I put 0 and 1 into that first version where I had solved for dy dx, notice I would get the same thing, that 0 over 3, and get the 0. But I didn't. But I got the same answer here without having to isolate dy dx first. So key goals today, guys, is take the derivative of everything before you put the point in. Now, after you take the derivative of everything, so once we got to this line, the 2x plus 3y squared line, anytime after that, you can put in the point 0, 1. Algebraically for us today, it will be easiest if you put it in right away. So let's look at, well, let me leave this here so you guys can see that while I pull up my next problem. And you guys, you'll also notice that the points that we have you put in, like 0, 1, that's a pretty easy point where x is 0 and y is 1. They're usually pretty straightforward points. You know, they're points that make it easier to solve the problem. So my next one, you guys, I've got 2x squared minus 3y cubed, I'm going to have to, yeah, equals 5x minus 3y. So I want to find dy dx for this problem, but I want to find it at the point, 0, 1 again. So remember, even though you have that point sitting there, and it's very tempting to want to put in those x and y values right now, because, you know, you think about it, you're like, oh, I have x is 0 and y is 1, that's going to make my problem so much easier. You can't put this point in until you take the derivative. I don't want to know what the function looks like at that point. That doesn't even make sense. You guys, I want to know what the derivative looks like at that point, what value the derivative holds there. So take the derivative of each term first. So let's start with the 2x squared. That's going to become 4x minus, let's do the 3y cubed. That's going to become 9y squared dy dx. You can't have that sound on in here, bud. You're going to have to turn the sound off. All right, so on the other side, notice how we have more involved on this other side than we have in the past. Almost, maybe all of our problems on Monday had a 0 on one side when we ended up taking the derivative. Notice we're not going to get a 0 this time. The derivative of 5x is 5. The derivative of minus 3y, be careful here, it's going to be minus 3, but you still have that dy dx. So notice we have dy dx in two different places. So you guys, it would be a lot harder to isolate it on this problem. So if I didn't have this point to put in and I just had to isolate dy dx as is, it would be a lot harder. I'd have to get them all on the same side. I'd be dividing by some kind of binomial term. So you guys, it's just harder. But because I've taken the derivative at this point, now I can go ahead and put in my point at 0, 1. So every x is a 0, every y is a 1. Let's see what happens. Well, here I'm going to have 4 times 0 minus 9 times 1 squared dy dx equals 5 minus 3 dy dx. So over here, nothing got subbed in because there was no x's and y's over there. But this 4 times 0 is gone. Make sure you carry this negative with you and get negative 9 dy dx equals 5 minus 3 dy dx. So once you put in that point at 0, 1 and all your x's and y's just turn into real numbers, your problem, the only variable left will be dy dx. Let's solve for it. So let's get them together on one side now. It's a lot easier at this point. So let's add 3 dy dx to both sides. And remember, dy dx acts like any other variable. So it might be a little bit confusing as we're doing this algebra on it, but remember, it acts like an x or a y or whatever. It's just a variable. So let's see what we have here, you guys. We have negative 9 dy dx plus 3 dy dx. So how many does that leave? It leaves negative 6 dy dx equals, and over here, we just have the 5. We're almost done. All we got to do now is divide both sides by negative 6. And we get dy dx equals, let's just call it negative 5, 6. So we put in a specific point, we get in a specific value. All right, so let's do another one. Let me pull up another one for us. All right, I want to do 7x squared y to the 5th. Let's see, I'm going to need some, I'm just going to pull it over this way a little bit. So I have 7x squared y to the 5th, and that equals 1 minus x squared minus y. I want to find dy dx for this at 0, 1 again. It's often 0, 1, guys. Getting rid of the x, putting it to 0 really helps, with the solving. So it's often something like 0, 1, or sometimes it's 1, 0, or you might see 1, 1. That's basically what we'll see here. So you guys, look at this. You guys, this is a product rule. You guys, so let's pull a u. Let's say u is 7x squared, and v can be y to the 5th. So du here is 14x, and dv is 5y to the 4th dy dx. So let's bring this down here. So let's take the derivative with the product rule here. It's going to be u dv. So 7x squared times 5y to the 4th dy dx plus v y to the 5th du, which is 14x. So this is the derivative of that side using the product rule. Now let's take the derivative of the other side. You guys, the 1 will go away. It'll be a 0. The minus x squared is going to become minus 2x. the minus y, you guys don't let just a y by itself fool you. Remember, if you had x, what's the derivative of x? Well, it's just 1. So the derivative of y is also just 1, but because it's a y, it's 1 dy dx. So minus dy dx. Okay, so we're here. Now, before I start trying to solve for my dy dx, because again, it would be pretty difficult at this point to get it together and get it by itself, this is where I get to put in my point. X's are zeros, Y's are ones. So guys, what happens here? You guys, if you put in a 0 for this X here, what happens to this entire term? Because it's all multiplied together, right? If you put in an X of 0 here, it doesn't even matter that you're putting in a 1 for this Y. This whole term is gone. So you guys, once you put in an X of 0, this term is gone. What other term is gone? You guys, if you put in a 0 for this 14. X, this term is also gone, the whole thing, because it's all just multiplied together. So on this whole side, when we put an X equals 0, we could just get a big 0 over there. Let's see what's on the other side. Well, we don't need to write that 0 minus, but you guys, what's going to happen to our minus 2x? That's also going to go, right? Because I put in a 0 for that x. All we're going to have left is 0 equals negative dy dx. So, you know, you can think about it if you want to. You could divide both sides by -1, so you can make dy dx positive. But this is still going to be 0. So you get your answer here. So we got 0, like we did on that first one. So you guys, just after we took the derivative and we did all that product rule on this one, it looked really complicated. But once I put in that point as 0, 1, look what it turned into. I mean, it was barely anything left, right? So a lot of things are like that today. You're going to be so happy that we have to put in a point. Okay, let me find another one for us. Let's do one with some e's. Yeah, let's do an e. Let's do 2x e to the 5y equals 2. So that's our function. We have 2x times e to the 5y equals 2. And this time, you guys, the point that I want to evaluate this at is 1, 0. So x is going to be 1 and y is going to be 0 this time. All right, so notice that this is product rule again. You guys, we have u can be 2x and v can be e to the 5y. So du is just 2. dv, remember how your e's work. You bring the term down as is. So we bring down the whole e to the 5y, but then we multiply by the derivative of 5y. What's the derivative of 5y? Well, that's just 5 dy dx. Because it was a y, we have to have that dy dx. Okay, so let's clean up, let's clean up this derivative of v. I'm going to put the 5 in the front. So I'm going to have 5 e to the 5y dy dx. I'm going to write it like that. If you don't, that's totally okay. It's just the way I like to see it. Okay, now that we have u and v and du and dv, we can use the product rule. So this is going to be 2x. So u times dv, so 2x times 5e to the 5y dy dx equals, no, not equals, guys. This is u dv plus v, which is e to the 5y, times du, which is just a 2, equals, you guys, on the other side, that 2 just is a constant, so it becomes 0. So before you do anything else, because we've now taken the derivative of every term, put in your point at 1, 0. So this time x is 1 and y is 0. So let's see what happens here. We get 2 times 1 times 5 times e to the 5 times 0 dy dx plus e to the 5 times 0, putting that y equals 0 again, times 2, equals 0. All right, so we have to know the exponent rules here. First of all, 2 times 1 is just 2. Here we're going to have 5e, so the 5 times 0 up here just makes 0. So we get 5e to the 0 dy dx. Plus, you guys, this is going to be another e to the 0 times 2. You guys, what's e to the 0? You don't have to know anything about e to know what e to the 0 is. It's 1 because everything to the 0 power is 1.
Someone needs to mute their mic.
25 to the 0 power is 1. Everything to the 0 power is 1.
Kevin, mute your mic.
So that means these two e to the 0s right here, those are just 1s. So let's put that in with those in there as 1s. So I get 2 times 5 times 1 dy dx plus 1 times 2 equals 0. So 2 times 5 times 1, that's just 10 dy dx plus 2 equals 0. And let's move your 2 over and get 10 dy dx equals negative 2. And then all you have to do is divide both sides by 10. So this one took a little more time, but putting the point in there did make it a lot simpler. I got chat. No, I don't want to stop recording. Every time I try to look at chat, it tries to make me stop recording. That is not what I said. Yeah, from which part? Like the e to the powers? Okay, yeah. All right, so let's take it. So you guys, I'm going to put in the point on this one. So I'm going to take it from this line where we took the derivative of everything. So the 2x, so after we took the derivative of everything, I got 2x times 5e to the 5y dy dx plus e to the 5y times 2. And then on the other side, I had equals 0. So this is just, the implicit. And we took the derivative of everything. And now I'm going to put in the 0.10. So every x is going to become a 1, and every y is going to become a 0. So when I put that in, I have 2 times 1. Then I'll have times 5e to the 5 times 0, because that y, each y is equal to 0. And then I have dy dx. Plus, so I have the e to the 5y. That's going to be e to the 5 times 0. And then that's times 2. And then that equals 0. So then from here, I simplified a little bit. So the 2 times 1, that's just 2. Now 5e to the 5 times 0. So I have the 5. 5 times 0 is 0. So what we get here is e to the 0. And then we have the dy dx. And again here, e to the 5 times 0 is just e to the 0. When you multiply those two together, they zero out. And then you have that times 2. So this is where I took the fact that e to the 0 equals 1, because anytime you take anything to the 0 power, it equals 1. So even if you had, like 1,000 to the 0 power, it's 1, because if you take it to the 0 power, it equals 1. So this is just, an exponential rule. It's not necessarily because it's an e here, it's because it's being raised to the 0 power. So because everything to the 0 power is 1, you can take this e to the 0 and this one also and just turn them into 1s, because that's what they equal. So in this next line here, I'm going to have 2 times 5 times 1, and I still have the dy dx, plus, instead of writing e to the 0 here, I just write a 1 again, and then that one's times 2. So here I have 2 times 5 times 1 dy dx, so this makes 10 dy dx, plus this 2 times 1 here is just 2, and that equals 0. And then from there, so from there, after you put your point in and get all this, you're just trying to isolate your dy dx. So we're going to subtract 2 on both sides and get 10 dy dx equals -2. And then our last step would be dividing by 10 to get that dy dx by itself. So that's -2/10, or let's reduce it and call it -1/5. Did that make a little more sense that time, maybe hearing it for the second time? Okay, perfect. Yep, you guys, anytime I need to slow down or you need me to re-say something, I can definitely do that. It doesn't hurt anybody to hear it again. Okay, so I can find dy dx at a certain xy point. You guys, I want to take this one a little bit further. So what we got was dy dx equals -1/5. Remember what the derivative is. No matter if we found it like this implicitly or explicitly, remember that dy dx, or the derivative, is always the slope of the tangent line at a specific point. So this -1/5 is the slope of a tangent line at this point 1, 0. If you have the slope of the line and you also have a point that it touches, you could find the equation of that tangent line. So remember, when we first started doing derivatives, we learned how to find a derivative, which was the slope, and then we took it a little bit further and found a point that was on the line, and then we used y equals mx plus b to find the equation of that line, the tangent line. So you guys, we can do that here, but it's actually even easier in this case, because they actually give you the point. You guys, we put in that point, the 1 and the 0. So you guys, if I were to take this particular problem a little bit further, and I wanted you to find the equation of the tangent line at this point 1, 0, it should be a pretty simple extra couple of steps. So remember, you know the slope of the line. The derivative is the slope. So that's okay. So you guys, the slope is -1/5. I just found the derivative at this point, and it was -1/5. So that's my slope. You guys, the point is right here. So let's remember what I did with that. So when you had the slope and you have a point on the line, remember you can take your y equals mx plus b, that basic equation form, and you can put your slope in there. So instead of m, I'll write -1/5 x plus b. And then remember, you don't know what b is. That's the problem right now. But even though we don't know what b is, we do have this 0.10 that you could sub in for this x and this y, and you can solve for b. So what does that look like? Well, it says that y is 0. So 0 equals -1/5 times your x, which is 1, plus b. So 0 equals -1/5 plus b. Remember, your goal is to solve for b here. So all you have to do is add 1/5 to both sides. And you'll just get, on this side, you'll just have 1/5 there. and you'll have positive 1/5 equals b. So if b is positive 1/5 and the slope of the line is negative 1/5, you can put that in the equation y equals mx plus b. So m is negative 1/5, and then you have x, and then plus b will be plus 1/5. So you guys, on this implicit stuff, because when it gives you a point to put in, it gives you both the x and the y value of that point. Once you actually find the slope or the derivative, dy dx, it's not a far stretch to go ahead and find the whole equation of the tangent line, because now you have the slope and it gave you a point on the line. So you use this solving for b technique, and then you can find the equation of the tangent line. So let's because there's some things you need to know about natural log that you might not remember. So I want to do x times the natural log of y equals 1. So let me put this in a different color. That might be a little bright. Let's do this one. Let's do x times the natural log of y equals 1. So this is our equation, and I'm going to find dy dx at the point 1e. Now, this is the point where x is 1 and y is e. And that might look super complicated to you right now. How do you put in e? You know, you have to sub the y's for e's. You guys, that e actually makes this point so much easier, and I'll explain it as we go. And if you remember anything about natural log, you probably can already see how this is going to make our problem easier. And if not, that is okay, because we'll talk about it. All right, so first of all, remember you first have to take the derivative of both sides. This x times natural log of y is product rule again. You're going to see product rule a lot with the u and v. You guys, so let's say u equals x. So du would just equal 1. So v, I'm writing this in a weird way. V is going to be the natural log of y. So the derivative of that, remember it's going to be 1 over y. And then because it was a y, though, you'll have dy dx. So let's find the derivative of this side using the product rule. It's going to be u times dv. So we have x times 1 over y dy dx plus v, which is natural log y, times du, which is just 1, equals, on the other side, you guys, the derivative of 1 is 0. Now, from here, this is where I put in my point. This time it's at 1 comma e. So x is 1, y is e. So let's keep that in mind. Let's put in x equals 1. So we get 1 times 1 over e. So I put in the e for the y. Then you have dy dx. Plus, you guys, natural log y becomes natural log e because I put an e in there for the y. And that's just times 1. I don't even know why I'm still writing that times 1. Equals 0. So here with the 1 times 1 over e, you can not have to write that 1 times because we know that's what that means, right? So we end up with just 1 over e dy dx plus, you guys, here's where we need to know what we need to know about e. The natural log of e equals 1. And if you're not sure why that's the case, remember a log statement. So the natural log is really just the log base e. So anytime you take a log and your base is e, instead of writing it as log base e, because e is a very special base, it has its own name. We call it the natural log, but it's the log base e. So if you remember anything about logs, and if you don't, that's totally okay. You can You can ignore this all you want as long as you remember this fact. But because natural log is log base e, when I say natural log e, that's like saying I'm looking for the log base e of e. And if you remember anything about how to solve log equations, log base e of e, what it's asking for is you take your base, you're looking for some power. You guys, you're looking for a power, let's call it y. And I'm saying that e raised to some power equals e. Well, what would that power have to be? So when you solve for log base e of e, because your base is e and your end result is also e, that power you're looking for ends up just being 1. So this is why the natural log of e is 1. And again, if this, you know, is like, wow, I haven't done that for years, that's okay. What you do need to remember is the natural log of e equals 1. So here, where I put in this e, I'm taking the natural log of e. I need to know that that just equals 1. So really, this is just 1 times 1, and we just get a 1 there. And then I have equals 0. So you guys, having that e in there for the y value, while no, we don't want to work with e if we don't have to, it totally eliminated your natural log statement. And that's a good thing. So you guys, from here, remember you're just trying to solve for dy dx. So you could subtract 1 on both sides and get 1 over e dy dx equals -1. And then to get dy dx isolated, you need to divide both by a fraction. It's the same thing as multiplying by the reciprocal of that fraction. So what I have is -1 divided by 1 over e, but I can write that as -1 multiplied by e over 1. So what's really left here, you guys, is just negative e. So negative e is your answer. That is the derivative of this function at the point 1e. And you guys, again, e's, you know, they're not our favorite thing, but remember, they're just constant numbers. E is not a variable, so you did just get a constant number as your answer. So it's still, you know, a valid single numbered answer. It's just that we call that number E instead of, you know, putting in what the number actually is. What is E, guys? If you don't remember, it's 2.71828, and it just goes on forever. Doesn't ever repeat, you guys, so it's irrational, like pi, right? So, you know, pi has all the decimals, and that's why we call it pi. E is the same way, that's why we call it E, to save ourselves the trouble of having to write a bunch of decimals all the time, right? So you guys, this one, so this one, let's see, hold on. Oh. So this one, not horrible. I mean, it did have the natural log in there, so you have to remember how to take the derivative of natural log, but it was a simple natural log derivative. It was the e part on this one, and you guys, don't let that throw you. Just remember, write this down because you might have to see it later. The natural log of e is just 1. Just like the fact, you know, e to the 0 or anything to the 0 is just 1. Another fact, if you remember it, it makes these problems a lot easier sometimes. Okay. So I think that covers any kind of problems that you're going to see. Remember, the homework for the first part of this section is already up. What you're going to see on this second part that I'm going to put up today is problems like this, where you do have to find the derivative and find it at a specific point. So most of your answers are going to just be numbers like -1/5, or what else did we find? We found 0 a couple of times, or -5/6. Because remember, once you take the derivative, when you put in that point, your answer is just a single number. So you're going to have a lot of them like that. You guys, there's going to be a couple where after you do find that derivative at that point, you're going to use that as a slope, use the point given, and find me the tangent line equation. So remember, that's an extra step that really just involves algebra, you know, remembering y equals mx plus b. And then, you know, there's going to be some e's, some natural logs, so you want to remember these facts here, and that will help you on those. But other than that, guys, that is 12.4 in conclusion. And then next time on Friday. Okay, so Friday, guys, we're still going to be Zooming. I have not, to be honest, a little bit surprising, but I haven't gotten any feedback from this class or my other classes. Nobody's told me that they want to be in person, and which is totally fine, guys. And I can see the appeal of, you know, just Zooming class. I've talked to a lot of you. You know, sometimes I have students whose schedules just make it easier for Zoom. Like if I have a few girls who have like softball practice and it's just easier. Yeah, it's just easier to just do it online and they don't have to get to campus and park and all that stuff. I have some people who, you know, work jobs that, you know, shifts can be all over the place, for example. So I've heard a lot of people tell me that it's really easier for them to do it this way. And because I have not heard from anybody who wants to, just really needs to be in class, I think we're just going to leave it like this, guys. And if for some reason, you know, it becomes a problem for anybody, we can definitely, you know, talk to each other about it. You know, we can always private Zoom meeting. Like if you're a person who maybe doesn't like to speak up and ask questions in a Zoom meeting or something like that, you know, we can always private Zoom meeting about stuff. I want to make sure this works for everybody, but I think at this point it seems to be, at least from what I've heard from people. So we're going to stay online. So on Friday, I'll be here. You guys, we're going to do the next section here on Zoom. And I think that's all I have for you. So I will just see you then.